So, hi everybody, welcome to Statistics 23, the normal distribution. And we're going to start off by talking first about the normal distribution's properties. And the properties that a normal distribution has are listed below. There are 5 of them. The first one is that the mean, which is that point exactly in the middle of the distribution, is equal to the median in the mode. And this can only happen if the distribution is actually symmetric. When you have a symmetric distribution, then you are able to see that that is a true statement. If your distribution is slightly skewed, then that's not going to be true at all. Normal curves are bell-shaped. In other words, they are shaped like a bell, sometimes stretched out left to right or sometimes squeezed up left to right. The other thing that's important about the normal curve is that the area, which is all this space in here under a normal curve, is equal to 1. Now what's interesting about that is that the horizontal axis is y equals 0, and the normal curve approaches it but never crosses it. So in other words, it goes on forever, and there's always a little space there, even though it's very small. But still, even though that space is infinite in size, it only adds up to 1. So the total area is 1. That makes this a probability distribution, which is an important fact. Y equals 0 is a horizontal asymptote. That means it doesn't cross the graph. And finally, the last thing is that on the interval from 1 standard deviation below to 1 standard deviation above, so it's this space right here, like that. If you look at the graph, then the graph up here is what we call concave down. It's curved down. But everywhere else, then the graph gets curved up. All right, has an upward curve to it, and that's called concave up. And those are the shapes of a normal distribution. Now, the most important thing for what we're going to be doing is using this fact that the area is equal to 1. Okay, next slide. Here's just a fact to kind of reinforce something. If the area is equal to 1 under a curve, then that means that the curve is a probability density function or probability distribution, which means then that you can use the area to help find probabilities. And that's really a key fact. Now, just so you know, in order to find those areas, you would need a formula for the normal curve. And I just wanted to show you that formula. It's also on the bottom of page 240 in your text. But if you look, it's the fraction 1 over the standard deviation times square root of 2 pi, e, which is the exponential number, raised to the exponent, negative x minus the mean, to the 1/2 over 2 times standard deviation squared. And I think it's very interesting. Pi is actually a number, x is the variable, e is a number. So the only real variables in here are the mean, mu, and the standard deviation. And so all normal curves depend exclusively on their mean and standard deviation. If it's the standard normal curve, then the standard deviation is equal to 1, and the mean is equal to 0, and you can see that that would simplify this formula quite a bit. Once you do that as a little exercise, come to class tomorrow with this formula simplified using the mean 0 and the standard deviation 1. So just rewrite it algebraically using those numbers in place of mean and sigma. you need a clearer picture of the formula, it's on page 240. Okay, that's just a little sidelight. So let's learn how we can use this to help us find area using the mean and standard deviation. So what we have here is I have the top two diagrams. Let me draw this little line here to separate the top two diagrams. What I want to show you something is how the properties of a normal curve help us here. Both of these are bell-shaped curves. In this one we have a mean of 5 and a standard deviation of 1. And since we know the mean is in the middle, it's right there. And then each standard deviation, we know that within one standard deviation it's concave down, and then everywhere else it's going to be concave up, and that's what we see in this picture. Now over here, if I continued this number line, dot, 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 and I went to 100, I have another mean and standard deviation. The mean is 100, the standard deviation is 1/2. Well, in this case, the standard deviation is smaller, so what happens is our normal curve gets squeezed together into a skinnier type bell. The bigger the standard deviation, the flatter the curve gets. Our mean is also larger, so it's much further on the number line than where it was before. But then in general, we have the mean right in the middle. Then this is going to be 100.5, 99.5, and there is where we're concave down, and then we are concave up everywhere else. And so these properties hold no matter what kind of normal curve you have. So your book on page 241 has an interesting example. They just want you to look at these three normal curves, A, B, and C, and they ask which one has the bigger mean, the greater mean, and which one has the greater standard deviation. So once you answer that question, and let me know. Okay, so that's right. The one with the greater mean is going to be this one, C, because it is way over here to the right. So its mean is bigger than the means of the other two. So the answer here was C. How about the bigger standard deviation? And that's right, the answer for that is going to be A, because A is more spread out and flatter, and therefore its standard deviation is going to be greater. Okay? All right, I hope that helps. So let's look at the next topic. So I have a normal distribution here, and this normal distribution represents the normal distribution for IQ scores. So what I'd like for you to do is interpret the picture for me. And in order to do that, you need to tell me some information based on what you see. Okay, so I'm going to pause the video. You figure out your interpretation. Okay, I'm back. So to interpret this, you would have just said, since, and this is how you would figure it out, since 100 is in the middle and normal distributions are symmetric, then the first part of my interpretation would say the distribution for IQ scores has a mean of 100 and I'll put and here. And then the next part that you want to interpret is what would the standard deviation be. So what I'm looking at is I'm looking where this is curved down, and it looks to be curved down, between these two values. So I would say that the standard deviation would be what? Correct. And a standard deviation of 15. All right. Now, intelligence scores don't have units, but say this was heights of redwood trees, then you would say the mean is 100 feet and the standard deviation was 15 feet. Okay? So some things have units, some things don't. So always remember the units. So that's the first interpretation. A second type of interpretation would be to find the line of symmetry and identify the mean. So in that case, the line of symmetry would be the vertical line through the value of the mean 100. If this was on a graph, you would say the line of symmetry is the line x equals 100 and the mean is 100. If you remember from algebra, vertical lines are x equals. What's an inflection point? Well, an inflection point is the point where a graph switches from being curved down to being curved up. And so in normal curves, inflection points, you write that word, inflection points always are one standard deviation above or below. So if I wanted to find the inflection points or estimate them, I would say that my inflection points were at 85 and 115, and then the standard deviation was equal to 15. And so that's also another way you can interpret, or at least find what your interpretation is. Last thing I want to talk about on this video is a review from last semester, and it is, what is a z-score? A z-score is a standardized numerical value that converts any normal set of data, any set of data that makes a normal distribution, and converts it to a standard normal standard deviation. And if you remember, the standard normal, the mean is 0 and the standard deviation is 1. So when we look at that curve, it goes 0, 1, 2, 3, etc., -1, -2, etc., with again the concave down portion, the concave up portion being outside 1 and -1. So a z-score, suppose I have a normal curve that looks like this, but the mean is 100. Well, then a z-score that corresponds to 100 is going to be 0. So I could take any one of those other kinds of distributions I drew, really flat ones, really tall ones, and their means will get converted to 0, and their standard deviation will get converted to 1 using this z-score. And so instead of saying, oh, somebody who weighs 180 pounds is 20 pounds above the mean, in standard normal language, we're going to say they are 1.2 standard deviations above the mean. And that's what the z-score is the 1.2 standard deviations. So it gives us a way to standardize everything and talk about that. Okay? That's all I have for now. You'll have a fairly easy assignment tomorrow, and then we'll challenge ourselves a little more the next day.